Before we begin any analysis, it's important to make sure that we have a working directory specified so that all the files we generate can be stored there. Now in this case, I'm going to do File, Change Directory, and I'm going to point to a folder which I've already created on the F drive called Laminate Plate Analysis. So I select that, click OK. And I also want to change the name of any files which are created to make them different from any others. So in this case it's File, Change Job Name. Instead of File, I'm going to call it Laminate. So every file that's generated from this problem will be called laminate dot and some extension. I will now also change the title for this analysis to Laminate Plate Analysis. Click OK. Now that title will appear in the bottom left hand corner of the window, but only when I start to create the geometry. So that's now our next task. So we go into the pre-processor phase, modeling, create. I want to create an area, rectangle, by two corners. So we're modeling a quarter of the plate, seeing as we have the advantage of symmetry. So my x and y coordinates will be 0, 0 at the origin. The width of the plate is 5 and the height is 5 as well. So click OK, and our area now appears. The next step now is to specify the element type we want to use. So I can close down the modeling tree, open up element type, add, edit, delete. Non-defined at the moment, so we click add, and we're going to model with shell 99 elements. So these are 2D elements. Just find it. So it's shell and linear layer 99, and click OK. If we wanted to, we could change some of the options, the way that this element works. These are some of the settings you can influence. In this case, all of the default settings are fine, so we'll just click OK on that. The element type's now been added, so I'll click close. Now the next important step is the real constants. So we click on real constants, add, edit, delete. We want to add. Our shell 99 element type appears, which is fine, so we click OK. Real constant set, it's already defined the default 1 value for this, so that's OK. Now the number of layers for this particular problem, it's 4. Now because we have a symmetrical layup, we can specify that here by changing that value to 1. And what this means is, instead of inputting the values for all 4 layers individually, we can just put in the top 2, and the simulation will take care of the rest itself. So we click OK. So we've said it's symmetrical, so we know our first top ply is 0 degrees, its thickness of an individual ply is 0.025, the second ply is at 90 degrees, again 0.025 thickness, and because we have specified symmetry, we don't need to enter the bottom 2, so we just click OK and click close here. So we're finished with the real constants, they can be closed. The next step now is to specify material properties. So material models, and this box pops up. It's a structural, it's going to be linear, elastic, and in this case we're looking at orthotropic material properties. So we now have Young's modulus, Poisson's ratio and shear modulus for 3 different directions. So we input our material properties. In this case, we input a value of 0.01 for the Poisson's ratio in the YZ plane. Click OK. So that's been done. We can close this box now. We have finished with material properties. We now want to mesh the problem. So we go to Mesh Tool. Now we will use the line set command to control the mesh density. So in this case, I'm going to put 10 elements along each length. So if I now pick all lines, the number of element divisions I want to input is 10. Click OK. And we go back into Mesh Tool now. So we've done this part, the size controls. We now want to mesh the areas. We're going to use quadrilateral elements and we want them to be mapped. So then click Mesh. Mesh the areas, so we just say pick all. And then that's it, we're done. So we've got 10 elements along each line there. Now at the moment, if I just change the view so we look at the oblique view, it's a two-dimensional problem and we have just a flat plate. An interesting feature to look at now would be to actually see what the real constant set looks like. So if we go on to plot controls, style, size and shape, and we're going to turn on E-shape, which is the display of the element. So we turn that on and we click OK. And if we now zoom into one of the corners, we can see now that we've actually got 4 plies. So if I now fit view, to turn E-shape off, just go into plot controls again, style, size and shape, and uncheck the box and click OK. And we're now back to just a simple flat plate 2D problem. All that's done is just shown us what real constants actually look like. The other thing that's useful to see when you're modelling composites is to actually see that the ply layup is as you specified it. So if you go to plots, layered elements, and now we just pick one of the elements, it doesn't really matter which, click OK. It's told us there we've picked element number 91. The range of layers, we can specify which number of layers we want to look at. In this case I want to look at all of them, so I can leave those blank and then just click OK. It then pops up with this screen which shows the layer stacking sequence, and I can see now I've got 4 plies with the correct layup orientation of 0, 90, 90, 0, and I can see that they've all been assigned the same material properties for material number 1. So everything's correct there. If I now want to see my plate again, if I go to plot, multiplots, it brings the main problem back to us. So the next thing to look at now is the solution phase. So I can close down the preprocessor now, open up solution. We want to apply loads and constraints. So the first thing we will look at is to specify the analysis type. So new analysis is going to be a static problem. Click OK. So we now want to define some of the constraints on the plate. So if we go to define loads, apply, structural, displacement. Now because we've modelled quarter of the plate, this line and this line are our lines of symmetry. So we can select symmetry boundary conditions, on lines, select the left and the bottom and click OK. and you can see little S's appear along the line to represent symmetry conditions. The boundary conditions for the top line are to fix UX and UZ. So first of all we select the line, click OK, and we will first of all fix UX, click Apply. We now want to select the same line again, click OK, and this time fix UZ. Instead of Apply this time, click OK, and that's taken care of the two boundary conditions which we wanted placing on the top line. We now want to apply constraints to the right hand side, so select lines again, click OK. We want to fix UI and UZ in this case, so fix UI first, click Apply, select the line again, and fix UZ this time, and OK. So there's our boundary conditions. We now want to specify the loading, so we can close down the displacement tree, and we want to now apply a pressure on areas. We select the area, click OK, and the pressure value is a 1, click OK. We're now ready to solve the problem, so I can close down the trees we're not using anymore, go to Solve, Current Load Step, click OK to begin. And click Close. So the solution has now been performed, so we can close the solution phase. We now go to the main third step, which is the general post-processor, to view the results. Now in this case we're trying to look for the maximum deflection in the Z direction, so we want to plot results, contour plot. I'm going to ask for the nodal solution. I want to know the degree of freedom solution with the Z component of displacement, and click OK. We can now see that the maximum deflection has taken place at the middle of the plate. Remember, this is a quarter model, so that's as we would expect it to be, and it's telling me that the maximum deflection is 0.068467, so that agrees very well with the analytical solution. Now the only final thing to do now is to make sure we have all of our work saved. So the easiest way to do this is to click on Save DB, and because we've already specified our working directory for the problem, if we now open up the folder, we can see that we have a file called laminate.db. This is the ANSYS database file. It contains all the information, and all of the other files here have been generated whilst the problem was being solved.